In this video, I went through my back catalog and found 12 different videos on piecewise functions. I hand-selected these problems to help you understand how to evaluate a piecewise function, graph a piecewise function, as well as find the value k that makes the piecewise function continuous. By going through these examples, you are going to have a strong foundation in understanding piecewise functions. I hope you enjoy.
All right, so as I was mentioning, at the beginning of the year, we did problems like this. We didn't talk about the limits, but all Harrison we looked at was, hey, I'm going to give you a piecewise function. Can you evaluate for f of -1? And I said, do not plug in -1 into both equations, because you guys have to understand this piecewise function is basically two functions combined together to make one general function. And each of these equations have domains that are restricted. And it's very important to understand the restriction. Now, we can be able to graph these, and I'll solve this problem with graphing. But you don't necessarily have to know what the graph looks like. But it is helpful. This is, let's graph 2x minus 1. Now, forget about the restriction for a second. 2x minus 1 has a y-intercept of -1, and then a slope of up to over 1, something we learned in Algebra 1. And then it looks something like this. Now, the domain is restricted. It says, I only want you to graph this or I only want this function to be used for values of x that are greater than 0. Well, the x values, the x-axis, is only greater than 0 when it's at the y-axis over, right? So everything to the left of the y-axis is negative x values, which are not a part of this function. You guys agree? So what I'm going to do is I'm going to erase that. And it also said x is greater than 0, not equal to. So I'm going to create a nice little dot, because it's an open point. It's not closed. The next one I look at is x squared plus 1. You say, oh, x squared, that's that nice little parabola. Plus 1 just means it's being shifted up 1, right? Well, rather than doing a perfect parabola, I only need to graph this for when x is less than 0. So if I was going to do a nice parabola here, I don't need to graph everything that's positive. I just need to do the negative version. OK? So again, what we're looking for is what is the value of the function at -1. And if you plug in -1 into both equations, it makes no sense to plug it in over here. Why would you plug -1 into that function? This function is only defined for positive values, right? So it makes no sense to plug -1 into the top equation. We only want to plug -1 into this equation, because this is the equation for all values of x that are less than or equal to 0. So all you guys had to do is plug it into this equation. -1 squared is 1, plus 1 is 2. Gotcha? OK. The next one, limit as x is approaching 0 from the left. Now, this is kind of related to what we did here, is if you guys look at this, from the left, which equation are we talking about from the left? The x squared plus 1, right? And the reason being is, for the left of 0 is all values that are less than 0. So that means this is going to be the left hand, right? You don't even need to know. I could give you crazy equations. And if you know, oh, x is less than 0, that's the left-hand notation, right? So again, I can just plug what value are we approaching. We're looking for the value that it's going to equal. So in this case, I'm just going to plug in 0 into that equation. So I have 0 squared plus 1 equals 1. And then for the right-hand equation, right, you would see if I'm approaching 0 from the right hand, I'm following this function, right? And the reason why is because all values that are greater than 0 are this one. So let's just plug in 0 there. Equals -1. Now, I want to show you some mathematical notation, because the last question I'm going to ask you, or the last question that's up there, is find the general limit. And remember, guys, the general limit only exists if the left and the right hand limits are the same, correct? So mathematically, it looks like this. The limit as x approaches 0 from the left of f of x has to equal the limit as x approaches 0 from the right of f of x. Now, thankfully, we already found the limit from the left, Mason, which was 1. And we found the limit from the right, which was -1. And since these are not the same, it does not exist. Now, again, you might say, Ms. McLogan, I can just look at the graph. Why are you showing this math? Well, because again, I did the graph for you. And I'm doing an easy examples that I could easily graph. But again, you could use the same understanding to apply to more difficult equations that you don't know what the graph looks like, right? And you could just apply the math from there, all right? But that's about it. The main idea, guys, is you have two lines in this equation. Again, we're trying to identify if it's continuous or not, and then describe the discontinuity. So we basically have two lines here. Let's just go and graph 2x minus 1. So forget about the restriction for a second. Let's just graph y equals 2x minus 1. All right, so I go down. That's my y-intercept. Up 2 over 1. And I can basically go in the positive direction, and I can go in the negative direction. So that is the graph. Now I'm going to go ahead and apply the constraint. And the constraint says, I only want you to graph this equation for x values that are less than 0. So that means 0 is not defined. So therefore, I'm going to put a nice little open circle there. And then it's only for x values that are less than 0. Well, here's the x-axis. Here's the negative x values. Here's the positive x values, right? So our x values that are less than 0 are only going to be to the left. That means I'm going to erase the rest of the graph that's in the positive for positive x values. Anybody have any questions or clarifying questions there? Again, this is not a time that you should be looking at your calculator. It's just a time for you to be looking up here. I know the stimulation of electronics is very difficult for many of you to overcome. But if you need me to give you a different seat that you can go ahead and pay attention to, then I'll be more than happy to do that for you guys. The next one is let's go ahead and graph negative x plus 3. This one has a different y-intercept, which is positive 3. And then we have a negative slope, so that's down and to the right one or up and to the left one. Either way, you guys are going to graph that looks something like that. We're not trying to be exact, guys, but what we want to recognize here is this is for only x values that are greater than or equal to 0. So therefore, it's going to be only for positive values. All right, and then, yeah, it's supposed to cross at 3, so I'll just be able. But either way, you can look at this graph and say, is it continuous? Can I draw the graph without lifting my pen or marker off of the board? And the obvious answer is no, it is not continuous. So therefore, we say, well, then what type of discontinuity is it? And you can say that is a jump discontinuity at x is equal to 0. Right? And one thing if you guys remember, if there is going to be a discontinuity, if you have two functions that are continuous, that is a continuous line, that's a continuous line, right? They are restricted, but both of these functions are continuous, correct? So if there is going to be a discontinuity, where is that discontinuity going to occur? At the restriction change, right? It's the only thing that would make sense. No, not always are we going to have continuous functions for each of the functions, but when we do, that's where it will occur, okay? What I can do is I can graph these two functions. And again, this goes to my point as far as just graph. You have, like I have pictures of them all over all the walls. You have notes on them. You shouldn't be able to sketch what the graph generally looks like. 1 over x, reciprocal function, is over there. For all values of x, looks like this. Correct? The square root function for all values of x is right over there. So that looks like this. Right? However, it's not asking us, or this function is not asking us to graph for all values of x. It's saying, I only want you to graph 1 over x when the x values are less than 0. So again, we got to remember, well, when are the x values, x-axis, less than 0? So that's going to be all x values to the left of the y-axis, correct? So that means this 1 over x function, this portion of it, is not within my constraints. So on my pencil, I'm just going to erase what I kind of drew. Then it says, and it's OK that it's less than because it approaches an asymptote. So I can just leave it like that. And then this square root of x for all values greater than or equal to 0. Well, greater than or equal to, so I'm going to use a closed point. And then obviously, the graph is already greater than or equal to 0. So there's really nothing else I had to do. Now, we should understand, though, this problem didn't ask you to do this, but I might, on a quiz or a test, hint, hint, wink, wink, ask you to determine the domain. So let's go and take a look at this graph and then domain and try to see if we can understand the domain and range. So we see that this graph is going infinitely to the left. So we go negative infinity. And then how far to the right are we going? Well, you can see that this graph doesn't go to 0, right? Yes? But this function does have a value at 0. So is 0 covered for a function? Is 0 covered for a function? Yes. So we can go negative infinity to infinity. The range, you can look at, this graph goes infinitely down. Even though this doesn't go to 0, we have this function does go to 0, and that goes to infinity. So the domain here and range is negative infinity to infinity. And the domain is negative infinity to infinity, and the range is negative infinity to infinity. So remember, on a piecewise function, the main thing we want to do is just graph both these functions so we understand. Remember, piecewise function, we're taking our two functions and we're going to combine them together. So what I'm going to do is I'm just going to graph both of these. So my first function is f of x equals x plus 2. All right, then my next function is going to be f of x equals 3x. Now you can graph these many different ways. You guys can use slope-intercept method. If you don't even remember slope-intercept method, you can make a table of values, right? Just make a table of values and plot them. However, for here, I noticed that now my y-intercept is at positive 2, so I'm going to go up 2. And my slope is 1 over 1, right? Because we can always write 1 times x, so it would be 1 over 1. So I'm just going to follow my slope. Up 1 to the right 1. Up 1 to the right 1. And you just keep on going up in that method. You can also go down 1 to the left 1. Down 1 to the left 1. Down 1 to the left 1 should be right there. There we go. OK. So I have that graph. So that's the graph for when the domain is for all x values, right? We say the domain for this, ladies and gentlemen, is from negative infinity to infinity, meaning the x value, this graph covers every single x value. Every possible x value has a value on this graph, correct? OK, I'm going to get back to that in a second. Now I need to graph y equals 3x. Here, my y-intercept is at 0, right? Because y equals mx plus b, b is 0. So here, I'm going to cross at 0. But now my slope is 3 over 1. So instead of here, when it was up 1 over 1, here I go up 3 over 1. Or you could also follow the slope in the negative direction and go down 3 to the left 1. Either way, you connect the graph going left and right. All right? So I put the arrows. The arrows represent that these graphs go to infinity, meaning I have an x value. No matter how far I go on this x-axis, I'm going to have an x-coordinate on this graph. So therefore, the domain for here is for negative infinity to infinity. All right? So ladies and gentlemen, a piecewise function, what we're going to do for that, our piecewise function is telling us, I want you to combine these two graphs. But you can't put these on top of each other. Otherwise, we wouldn't have a function anymore, right? Because look at 0. At 0, I have a y value at 2. And here I have a y value at 0. So I have two different values at y, or two different values at when x equals 0. So therefore, I do not have a function when I combine these. So I put constraints on them. Rather than having domain negative infinity to infinity, I only want to graph this when x is less than or equal to negative 2. So I go over to negative 2, and I say it can be equal to negative 2 or less than negative 2. But that's it. So everything that's greater than negative 2, bye-bye. Well, no, what is the domain of this? The domain of this now is x is less than or equal to negative 2. Do you see? See how of this function. Domain of this is now x is less than or equal to negative 2. Then the next thing I look at, Amber, is I look at this one. This one has a domain of negative infinity to infinity, but I only want to graph it when x is greater than negative 2. So I look at when is x greater than negative 2. Well, it's going to be a big open circle right here. OK. So it's going to be when it's greater than. Hello.
I'm just delivering your candy. I'll just put it over here. Is that okay?
OK, that's fine. So I have when my x is going to be greater than negative 2 is going to be open right here. Now it says greater than, not greater than equal to, so that's why it's an open dot. So all when my x values are less than negative 2, that means all the x values to the left, that's now going to be what? Erased. So do you guys see how these two, look at my domain. The domain for this one is what? X is greater than negative 2. So do you guys see how my domain changes? Now the domain for this graph is all x values greater than negative 2. The domain for this one is x values are less than negative 2. Do you guys see that? Now what we do is we just put those two graphs together. So now I'm just going to graph them on the same set of axes. So I look at this and I say, all right, -2. So I go down, it's cross that there, so I go down 1, over 1. Looks something like this. Then over here, this point is at -1, 2, 3, 4, 5, 6 over 2. 1, 2, 3, 4, 5, 6 over 2. There's going to be an open dot with a slope of rise 1, 2, 3 over 1. Rise 1, 2, 3 over 1. Cross right there. And there it is. Now we look at the domain of this function. Does my domain now include all x values again? Yes, right? Because if you look from all the way here, this goes all the way to infinity. So yep, I have an x value, I have an x value, I have an x value, I have an x value. Yes, I do have an x value right here. I don't have an x value for this function, but my x value for there is good. Then I move over, and now I don't have any more x values for this function, but I go down, and now my x values work again for this function, and it continues all the way to positive infinity. So the domain of this piecewise function is -infinity to infinity. It's the combination of the two functions. Yes?
You have to find a domain from like the function separately and then.
No, it's going to be the whole function together as a piecewise. Okay? If we are going to go ahead and take a look at this one again, it's very important for us to just kind of think about graphing these separately on the same graph and then just using our constraints to go ahead and finish them up. So you can think of y equals 2 times, 2x minus 4 squared. Well, again, minus 1. Again, what I said is whenever you have a compression or reflection inside the function, but you also have a translation, you got to make sure that that is being multiplied by both of them. So I need to factor out a 2, which leaves me with an x minus 2 squared minus 1. So now when I go ahead and graph this, my vertex is now changed to over 2, down 1. Please note that that horizontal, so now it's basically being a, was it a horizontal? We said a stretch, horizontal stretch. No, it's a vertical stretch, horizontal compression, right? Yeah, I'm sorry, horizontal compression, horizontal compression. But what that's making us do is basically going over 2, over 1, up 2. And over 1 up 2. And that is less than or equal to 2. So you can see that it's skinnier, right? And you could have also gone over 2 instead of going up 4, up 8, because you're multiplying it by 2. But we don't need to get very specific into that stuff. Last one is the square root function, which is y equals square root of x minus 2. What you guys can see is a transformation to the right 2 units, but then up 1. OK, and then that is just a nice little curve, looking something like that. However, that's greater. So that's only for values that are greater than 2. Well, 2's here, so all values are greater than 2 are over there. But that's greater than, so it's an open circle. And then I have my y. This value is only for x values that are less than 2. So then all of that gets deleted. So then you're left with that nice little function. OK?
All right, what I'd like to show you is how to graph a piecewise function. Given this function, I'm given kind of 3 expressions, and I'm given 3 constraints. So all a piecewise function is really kind of 3 different now lines that we have to graph, and now they have constraints on them. Because usually when we graph linear lines, they go from -infinity to infinity, and for both your domain and your range. But now what we've done with the piecewise functions is we've made constraints on our lines. So what I'm going to first do is I'm going to rewrite each one of these expressions in a y equals mx plus b form, so then I can just kind of get my mind set up in what they actually mean. So this graph, this expression would be y equals a -1. This would be y equals 2x. And this could be read as y equals 6. So now I'm starting to think of these. I need to say, all right, well, if I remember my y equals mx plus b form, I need to say, all right, what is going to be the y-intercept for each one of these equations, and then what is going to be the slope? If I look at this first one, I notice that there is no x, so therefore I have no slope. And my y-intercept just got to give me a -1. Therefore, this is going to be a constant line at -1. Now, when graphing a linear equation, I notice that I have constraints. This graph is only true when x is less than or equal to 0. Okay, so I'll write it. So what I can do, there's a couple ways you can do it. You can just graph it as when it's only true, or you can maybe just graph the whole equation and then start erasing where it's not true. And I'm going to go through that just so you guys can kind of see what the whole graph will look like. So I have x equals -2. Actually, Samantha, could you look at my? Actually, you see that red marker right in the folders? In my folders to the right. You see a red marker. Yep, just throw it. What's that? Well, underhand toss it.
You know you're making a video, right?
I know.
I know.
Okay. So if I was going to graph this at -1, I'd go down to -1. All right. Then I say, all right, it's only true though when x is less than or equal to 0. Well, where x is 0 is right at the y-intercept. So therefore, this graph, I'm only going to shade in where it's true. We're not going to draw where it's false. We don't care about where it's false. We only care about where this equation is true. So it's only true when x is less than or equal to. Since it's equal to, it's going to be a closed circle. Next point, y equals 2x. What does that graph look like? Well, I know that my slope now has a slope of 2/1, and I do not have a y-intercept. I'm sorry, my y-intercept is 0 since it's not labeled up there. So I do have y-intercept at 0, but it's not shown in the equation, so therefore I know it's 0. So therefore, on this, to graph it, if my slope is now 2/1, that means I'm going to rise 2, go over 1. Rise 2, over 1. So now we're down 2 to the left 1, and down 2 to the left 1, and then down 2 to the left 1. So again, I'm just going to dot a line, just so I know, just so I approximately know what my graph is going to look like. Then it says, however, this graph is only true from 0, when 0 is less than x or less than or equal to 3. So therefore, since it's just less than, I know it's going to be, since it's just x is greater than, it's going to be an open circle, and it's going to be between 0 and 3. So I'm going to go over 3, 1, 2, 3, and I'm going to follow that up to my graph. And now this is going to be x is less than or equal to 3, so it's going to be a closed dot, and I'm just going to shade in this graph here. So that is between 0 and 3 is only when this equation makes sense. That's the only time that equation is true. All this values over here and these values over here, it's not true under these constraints. So I'm not going to include them in my graph. And then lastly, I have y equals 6. Again, it's just like y equals -1. The y-intercept is at 6. And it says it's only true when x is equal to 0. Or I'm sorry, x is greater than 3. So therefore, at 3 again, I'm at my 3. That dot really should be up there. Sorry guys, I don't have graph paper on my board, so I gotta be close to as proximate as possible. And x would be at 3. One, two, three. And x greater than 3, this lot would look like this. However, I'm only concerned about when it's greater than or equal to 3. So it's roughly going to be right there. I understand from home, you guys can see that, my graph right here is not going to be the best in the world because I'm just making up my scaling is not exact. But your graph should roughly look something into this format. And now, guys, you can see the blue is all I'm concerned with. So I'm just going to simply just erase away my red. because those are points that do not meet the constraints of my piecewise function. So there's no point in having them on there. I just use them as a template to graph my rest of my equations. All right. So that is how you graph a piecewise function when given your equations and your constraints.
So when you're doing a problem like this, again, you have 3 different functions. Now, what I would recommend a lot of times, guys, when you're trying to remember how to graph functions, looking at them in a piecewise function sometimes gets confusing. So what you can do is think about them as, well, let's write this as like a y equals -3 minus x. Can you graph that? And some of you might even say, well, I still have having trouble looking at knowing how to graph that. Well, think about that in terms of y equals mx plus b. Rewrite it so it's -x minus 3, and y equals -1 over 1x minus 3. Now that's in mx plus b. You can see that m is -1, right? -1 minus 3. Now that's a little bit easier to graph. If you're going to look at this one, y equals 4. How do you graph y equals 4? Well, if x is equal to 0, what does y equal? 4. If x equals 10, what does y equal? If x equals -1,000, what does y equal? 4. So y always equals 4. So here's the y-axis, 1, 2, 3, 4. Y always equals 4 is actually pretty easy to graph. It's horizontal. If x equals 4, then it'd be a vertical line at when x equals 4. Let's go and graph this now. If you guys remember, my y-intercept is at -3. 1, 2, 3. And then my slope is negative. So therefore, it's going to be going down like this direction. So I can either say it's going to the right one, down one, or I can say it's going up to the left. And then my last one is another quadratic. So again, that goes here, over 1, up 1, over 2, up 4. 1, 2, 3, 4. OK? So again, I graphed. All I did was graph identity functions, except this one had a little bit of transformation, or this one, was a line. But we practiced graphing lines. Now, again, let's just follow the constraints. This one says only graph when x is less than or equal to 0. So again, here's the x-axis. The x values are greater than 0 to the right of the y-axis. Would everybody agree with me? So that's 1, that's 2, that's 3. So since these x values are positive, they don't fall within that constraint. So I'm going to erase them. Then this one says only graph y equals 4 between 0 and 4. But it's less than, right? It's not less than or equal to. So those are now open circles. So between, oh, shoot, that should have been 2. Sorry, I did make a mistake. That should be 2. So between 0 and 2. So therefore, this is now an open circle between 0 and 2. And that is an open circle. Everything else on y equals 4 is no longer graphed. Does everybody follow me? Anybody have any questions? Want me to stop? Re-say something? Good? OK. I'm sorry? So x is greater than 0. X is less than 2. So x represents the function, which is less than 2. So it's to the left of 2. But it's greater than 0, so it's to the right of 0. Does that make sense?
So you should erase those two.
Which one? Here?
No, the other side.
What other side? Here? On top. Yeah. To the left where?
Yeah, shouldn't that be erased?
This? Yeah, but that's for this function, though. I haven't got to that constraint yet. But yes, we're going to get to that. Yes?
Okay, so if it was like that was like that, and then
That was like that. What do you?
that 0 and then is less than x, or x is greater than 0 but less than 2.
Yeah.
If it was x is less than or greater than 0 and then greater than 2, would it just be like that part you have there? The segment wouldn't be included in the next one?
You mean if there was an equal sign under there?
No, like
If this sign would flip.
yeah, just one.
OK, well, I mean, if it was, if you had like 0 is greater than x and then like that,
Yeah.
OK, well, then that says x is greater than 0 and x is greater than 2. So yeah, I just continue going on to the right.
Oh, I think he wanted you to flip the
Okay. So like that.
Then you have to move the second thing back. 'Cause then
Okay.
now it would just-
So now that's saying x is less than 0. So that's all values that way. And then x is less than 2. So yeah, it'd just be all values going to the left from 2.
Isn't there like a way that you can like have like a spot though where it's not?
You mean where it's going in like in opposite directions? Like x is less than 0 and x is greater than 2?
Yeah.
Yeah, I mean, I could write it in like that. X is less than 0 and x is greater than 2. So that's saying that would look like this. An arrow going this way and an arrow going that way. And that's possible. That's just not what the constraint is, though. But yeah, that's possible. You could have that. Okay. Now let's get to the last one, x squared, where x is greater than 4. Shoot, that's supposed to be 2 again, too. Sorry about that. So then x equals 2 is going to be from here over. But that's greater than equal to, so that's filled in. That means all the rest of the graph is erased, because it's only for values that are greater than 2. Sorry, I made up the problem, so that's why it looks. But that's the graph. Now, the important thing is the reason why these constraints work, because is this a function? Does this function pass the vertical line test? Yes, right? But if you had a line going like that, it wouldn't pass the vertical line test. It's no longer a function, correct? So that's why it's kind of important making sure that you're eliminating those constraints, because those constraints allow us to produce a function. But it's just a piecewise function. Yes?
So when would you know that it's a function or not?
As long as it passes the vertical line test. When you create a vertical line, as long as it passes the function at one point, it passed the vertical line test, it's a function. If you had another line going like this, it would cross the function twice, therefore it would not be a function.
Okay, so if it's crossed twice, not once, or crossed
Correct.
once,
Correct. Now let's go and look at the domain. Does the graph continue to the left?
Yes.
Does the graph continue to the right? Yes. The domain is all real numbers. So domain, we can say negative infinity to infinity. The range. How low does this graph go? Negative 3, which is included. So that's a bracket. Well, negative 3 is a point on the graph, right? Whereas the other problem, it was an arrow, so it was infinity, so it wasn't included. But negative 3 is a point on the graph. Whereas here, that's not a point, because that's an open dot, right? But that's a solid dot, so it's a point, so it's included. So that's negative 3, and then it goes up to infinity. But yeah, if I change this, if I made this look like this, then that would be a parenthesis. So in this example, ladies and gentlemen, the main important thing is we need to make sure we know all of these graphs as well as their transformations. All right. So first of all, the first function is exponential. If you guys remember the exponential function, kind of over here, exponential function has a y-intercept at 1 and looks something like that. So if taking this graph, you can see I'm adding 1 outside the function. So I'm basically just shifting the graph up 2 units. Okay. Now, also, there's a horizontal asymptote here that's being shifted up as well. So the graph is not going to cross 1 because that got shifted up. So the graph looks something like this. Again, when I pass back your guys' quizzes, you'll notice I didn't mark you down for not having perfect graph, but you should have the general shape of the graph. Now, this says only graph this function for x is greater than 0. So x is greater than 0 is only positive x values. So I'm going to delete all of this. And I'm going to make this a nice hole. Anybody have any questions on the first equation? Good. Second equation is a line. Whew, you guys should like lines. Line. Okay. Slope 2 over 1, y-intercept 2. Go over to 2, up 2 over 1, or down 2 over 1. All right? So the line looks something like that. Now, the problem with this line, though, is that it is equal to at 0, so that now gets filled in. But its x is less than or equal to 0. So even though that's equal, nothing greater than 0 is a part of this graph. So I'm actually going to remove that portion. And then it says x has to be greater than negative 1. Well, here's negative 1. Here's positive 1. So x is greater than negative 1 only from moving to that portion. So therefore, all of that gets done. But it says x is greater than negative 1, so that's a hole. Everybody see that? Now, moving to the last one, which is a quadratic, which again, you guys should be very, very familiar with the quadratic. Looks like this, right? But what is happening in this graph? You have an x plus 1. Do you guys see that I'm adding a 1 inside the function? See, it's inside the x squared, so it's affecting the x squared. So it's inside the function. X plus 1 is going to be shifting my graph 1 unit to the left. And it says x is greater than or equal to -1, so it's going to look something like that. However, it says only graph x for less than -1, so that's equal to. And then it looked like something like that. Okay? Now, this is a continuous function. So if we were going to look at the domain, you guys could say the domain is -infinity to infinity because this graph is going to keep on expanding. And then you guys could also see that the range is the lowest the graph is going to be at 0, which is included, and it's going to go as high as infinity. Okay? Cool. We're going to look at these from two different perspectives. First perspective is just the graphical approach. So if I want to find the value k that is going to make these continuous, based on that last example I talked with you, it might be obvious. It might not be obvious for some of you. So my recommendation to you is, well, let's graph what we know. Let's graph 1/2 x minus 3. 1, 2, 3, up 1 over 2. That graph looks something like that. Correct? And that's only for values that are x is greater than 0. So it's only going to be going from there, and that's an open circle. Now, I don't know how to graph this when I don't know what k is. So let's give k something easy. How about 0? Can I graph y equals, like if I remember this, can I graph -3/2 x from there? And it's only going to be graphing it for values that are less than or equal to 0. So that means instead of going down and to the right, or it's negative, right? So therefore, I'd have to go like up and to the left. So I could go up 3, 1, 2, 3, down over 2. And it's going to be less than or equal to 0. So if you look at these, right now, if k is 0, the function is not continuous, right? So I basically need to move this function down 1, 2, 3 units. So then what value of k would make that shift down 3 units? -3, because that's just the y-intercept, right? So -3. So k equals -3. Now again, I'm only showing this to you because you're like, all right, that's kind of obvious. That's an easy one, right? But again, the reason why I want to do this is because I want to bring you guys to this algebraic approach. These are discontinuous right now when x is equal to 0, right? So if we want them to be continuous, we want them to be continuous when x is equal to 0. Not 5, not -7. X is equal to 0. So if they're going to share the same x coordinate, if they are connected, that means their y coordinates need to be the same as well. So all you're simply going to do is set both equations equal to one another. And then when x is equal to 0, you're just going to replace x with 0. And when you guys simplify this, you get the algebraic answer. So when you want to find the value k, we're looking at this graph, and we know that it's not continuous at 1, right? So what we're going to do is, to make these continuous, we want this graph and that graph to be the same, right? We want that graph to go down, so it's exactly the same right there. Everybody agree? We want to shift that down. We don't want it to be at +2. We want it to go down. So what we need to figure out is, whatever value this is, we know that it has to be the same. So the first thing I'm going to do when we want to find this k, and again, guys, it doesn't matter what these equations are. Take 1/2 x minus 2, set it equal to -x plus k. Set them equal to. They have to be equal to each other. If it's going to be continuous, whatever the left side graph and the right side graph have to be the same. Correct? They have to be equal to each other. Now that they have to be equal to each other, what value of x are we trying to make them equal to each other? And what value of x are we trying to make them equal to each other? Where are they trying to meet at? Well, we don't assume you don't know the y value. What x value are we trying to make? Now again, -2 is the y value, but there's nothing for y. And what x value are they trying to meet at? Yes, Carol. 1. At x equals 1 is where they're going to connect, right? So what we're going to want to do is plug in 1 in for x. And again, the reason why 2, I wouldn't say it just because you know, like you're saying that because you can see it. But imagine if I gave you something really crazy, you wouldn't know where they would possibly connect. The only thing you would know is 1, and 1 is always going to be obvious because that's part of the piecewise function, right? If I change this to 3, then you put 3 in for the x's. Does that make sense? Right? So now all we got to do is solve for k. And I chose a problem that we have to deal with some fractions because I like you guys that much. So 1/2 minus 2 equals -1 plus k. So I add 1 to both sides. 1/2 minus 1 equals k. Well, 1/2 minus 1 is going to be -1/2 equals k. So what that means is, if this graph, and actually, yeah, you don't even know that's the y. That was the y-intercept, was that -2. You actually don't know where that y value is right there. But it ends up being, if you had this y-intercept at -1/2, if you guys were to graph these two now, they would be continuous function. And that's what the k is doing, okay? Again, just a reminder, guys, let's go ahead and plug in this. Let's go and look at this graph. This has a transformation of 2 units to the right, and then 1 unit up. So 1, 2, up 1 unit. Should look something like this. But again, it says x cannot equal 2. So you go to 2, you say there's a hole there. Then they're saying it equals 2, but what value do we want k to equal 2? Yeah, we basically want k, well, we basically want k to then be equal to 1, right? If you guys agreed, if we had 1 there, and if k is equal to 1, then we can go and figure that out. Now, all I have to do is, again, as I mentioned, change this to cosine of x minus 2 plus 1, and then I can confuse all of you, right? So the functions are going to change. I'm just doing some basic examples for you guys to understand. So no matter what the function is, exponential, logarithmic, absolute value, no matter what the function is, all we're simply going to do in this case to find the value k. Now this is obvious because we're looking at the graph, but I want to show you guys algebraically what we're doing. We basically want our function to equal that value, right? Because when you guys take a function, you know, x minus 2 squared plus 1, we set that equal to y. X is the input, y is the output, right? So we want that output is going to be where that hole is. We want to know what is that output. So k is what we're trying to find. Okay, and then again, what are we trying to find k at? We're trying to find k when x is equal to 2. So all we're simply going to do equals plug 2 in for there. 2 minus 2 is 0. 0 squared is 0. K equals +1. Again, I showed you guys the graph. It was obvious looking at the graph, but you guys need to make sure you know how to do the algebra for that. Okay?
All right, what I'd like to show you guys is when given a piecewise function, how to write actually what the function is. So how to write a piecewise. How to write a piecewise function from a graph. All right. First of all, what we need to do is we need to determine what are our 3 equations. Because you have 3 different lines, all with different constraints. So we need to determine what are our 3 equations. So what I'm going to go ahead and do is I'm just going to start left to right. I look at this line. All right, this is a straight constant line at 6. So I know when I have a straight line, I have no slope. Therefore, my slope would be 0. So therefore, this is just going to be a constant term. And the constant term, I know if I was to continue this line with no constraints, it would cross at 6. So therefore, this line is y equals 6. That's how you'd graph that line. Then I look at the next one. If I pretend this graph had no constraints, I could continue this infinitely to infinity and negative infinity for the domain and the range. And I notice that this would cross at 4. And it also has a slope of down 1 over 1. So therefore, I'd get y equals negative x plus 4. Lastly, I have this equation. And I see that this one, since I'm going, my intervals will go by 2, I would say this roughly intersects at 1. And my slope is, let's say, up 2 over 4, which also could be reduced down to 1/2, right? So I'd say this slope is y equals 1/2 x plus 1. So now, here's my three equations. And I need to say, all right, well, now let's go and look at what are the constraints per equation. Here, it looks like these are going by 2, 4, 7, 6. This one looks like this is true for only numbers that are less than 5. So I'd say x is less than 5. And the one thing I notice is that this has a closed dot. So therefore I know it's also going to be equal to, -5. Then this one has an open dot at 5, and it goes from 5 to -2. So I'd say this one goes from -5, which would be less than x, which would be less than -2. And lastly, I have -2 all the way up to infinity. So what I would say for this problem would be x is going to be greater than or equal to -2. So the main important thing, guys, is to write your three equations and then you're finding your three constraints. Then you can put it in your piecewise format. Which for this equation, I'd write f of x, and I'd say 6 if x is less than or equal to -5, -x plus 4 if -5 is less than x, which is less than -2, and 1/2 x plus 1 if x is greater than or equal to -2. So that is how, when given a graph, you write it as a piecewise function.